Thank you, and I want to thank the organizers for the invitation and congratulate them for organizing a very interesting conference. I'm getting up at 3 a.m. every day, and I find that I constantly hear about things that I was unaware of. I'm quite impressed with some of the things that are going on. So, as the chair indicated, this is a topic that people have been arguing about for at least the past century. And I'd like to get in my 2 cents, which changes every time I learn something new. So this is not the same talk I would have given several months ago or even several weeks ago, as I think more about it. Smooth. Now, what happened? Okay, there we go. I have many collaborators on this in this field, but particularly today I'm going to talk about work from 2 students who've just finishing up their papers now. One, Unruh Rinehart, will defend his PhD next week, and the other is an undergraduate, Timothy Bunch, who wrote an undergraduate paper that has already been submitted. And these documents will eventually be available through the Texas A&M University Library, but it will take about 6 months for them to filter through the bureaucracy and get installed there. I had intended to talk also a little bit about some work that I did in the past few years with a group in Sao Paulo, led by George Matsas, relating this classical charge situation to Unruh detectors. But I realized I would not have time to get that into today's talk. And my work in this area in recent years has been strongly stimulated by developments within the quantum optics group at Texas A&M, led by Marlon Scully, and the many visitors that he is able to bring into Texas A&M. So I would like to mention especially a former student of mine, Justin Wilson, who co-authored a paper that I will talk about briefly later on, and another long list of people whose names are well known to you. And as the chair indicated, this is something that people have been talking about for a long time. And I realized I forgot to put in a slide giving the outline of the talk. So let me just say in words how it's going to be organized. There will be 4 parts. The first part consists of some general remarks about the relationship between acceleration and radiation and some indication of why there are so many controversies. Although there are many controversies that I won't even reach today because I had to be very selective to get talk into an hour. Then the second part will discuss the principle of equivalence, and that will sharpen the controversies. It will either, depending on your point of view, it will either relieve the contradictions or make them worse, depending on what you believe. Then in the third part, I will turn to the exact solution of the retarded solution for a charge that is a point charge that is moving with uniform acceleration for all time, and look at it and see, well, is there radiation or isn't there? And under what circumstances, for what observers? And following the thesis of Unruh Rinehart, I will present evidence that we do know how the radiation depends on the acceleration of both the charge and the detector in an extremely nice and symmetrical way. and it will verify the equivalence principle, provided one accepts the definition of radiation. And then finally, in the fourth part, I'll discuss the definition of radiation that leads to this conclusion and indicate some ways in which there may still be some loose ends that need to be cleared up. So let's get started. The story begins, I suppose, with Larmor in the 19th century, who showed that an accelerated charged particle will radiate. This is sometimes called Bremsstrahlung. The charged particle radiates electromagnetic waves of a total power that is proportional to the square of the acceleration. This, as stated, is a non-relativistic formula, but it remains true in special relativity if you replace the acceleration by the acceleration 4 vector, which is the derivative with respect to proper time of the velocity 4 vector, which in terms is the derivative with respect to time of the position. So replace the a squared there by a mu summed, and you get the relativistic formula. If the acceleration is uniform and lasts for all time, then the world line is a hyperbola in space-time, and its asymptotes are what we now call horizons. Although Larmor, of course, did not use the term horizons, nor did the physicists of the 2 generations that came after him. The significance of horizons developed only in the 1960s or thereabout under the influence of general relativity. The basic observation is that if the charge is confined to this hyperbolic path on the right-hand side, then the asymptotes of that hyperbola divide space into 4 quadrants. You should imagine these asymptotes as planes, because I'm suppressing the 2 transverse directions, which we'll call x and y. But there will be a region on the right-hand side where the charge lives, which is labeled R, standing either for right or for Rindler, because it's called Rindler space. And there will be a corresponding left space and a past sector and a future sector. And the fundamental causality of the situation is that if you start out with no radiation except that which is given off by the charge in a retarded manner, then there should be no resulting radiation in the regions L and P. So radiation should exist only in F and R. And it turns out that what happens in R turns out to be subtle. There is a sense in which you can say there's no radiation in R either, that the radiation is detected only in sector F. But that's a gross oversimplification of what we'll discover. And let me stipulate once and for all that the charge is forced to move on this hyperbolic path, come what may. So I'm not saying anything about reaction back on the behavior of the charge. I won't discuss the equation of motion of the charge today at all. And it's to be understood that the charge moves in this hyperbolic path, and the energy from the radiation comes ultimately from the agency that maintains that acceleration. So energy conservation is not an issue. And now the controversies there are 2 of them that are really important that I want to concentrate on today. The first question is, our charged particle may be interpreted by a co-moving observer as being at rest in a static gravitational field. So does that observer observe any radiation coming off? While you're thinking about that, let me remark that by co-moving, I really mean following another orbit of the same Killing vector. Or to put it another way, another hyperbola of the same Rindler coordinate system. So if we look at the cartoon on the left, you'll see that the 2 hyperbolas in question are confocal. and share the same asymptotes, but they're not of the same curvature. You sometimes, a lot of the literature on this subject is very vague about what co-moving or co-accelerating means. And in at least one paper, I see a drawing that looks like the one on the right, in which one of the hyperbolas is exactly congruent to the other one, but displaced in a horizontal direction, so that the asymptotes of that hyperbola would not be the same as the asymptotes that I've drawn. That's absolutely not what I'm talking about. Of course, if you go out into the transverse directions out of the plane of the picture, then the hyperbola will retain the same shape. But if it moves around in the direction, the z direction, where the direction away from the horizon, then it must change in order to keep change its shape in order to keep the right asymptotes. Otherwise, the situation is more complicated than what the equivalence principles speaks to. So before we answer this question, maybe there's a previous question that we should dispose of. Question 0, does a uniformly accelerated charged particle radiate at all? Does it radiate from the point of view of an inertial observer? The consensus answer nowadays is yes. But historically, over the past century, at various times, many respectable physicists, including Max Born, Pauli, Feynman, Unruh, at various times said in print that the answer was no. And there is a man named Ashok Singhal who still says no to this day and frequently publishes papers along this line, which to my taste have not yet been firmly refuted. So as editor of a special issue of a journal, I accepted his paper recently because I couldn't find any referee who would say it was wrong. But for today, I take the point of view that a uniformly accelerated particle, a charged particle, does radiate according to the Larmor formula. Is there some kind of an observer-dependent effect when you consider non-inertial observers or non-inertial detectors? So I restate the question. If you have a co-accelerating observer or detector, does it observe the radiation in this situation? And there is a strong consensus answer that is developing that the answer is no. And although I have not put lots of calculations into this talk, I hope that we'll be able to see why that is the natural answer. But first, let's look at question number 2, which is even more interesting. Suppose we have a charged particle in inertial motion, in particular, a charged particle at rest. Then it may be interpreted as an accelerating observer as being in free fall in a gravitational field. Does that mean that this fixed particle is radiating because the accelerating observer says it's being accelerated by the gravitational field? That question is a lot more controversial. A lot of people say, obviously not, but there are various strong arguments for yes. And one such argument is the one that brings us this question into this conference. This phenomenon, assuming it's correct, would be a classical counterpart of the Unruh effect, that an accelerating detector sees thermal radiation in the vacuum. In the classical problem, there's no thermal radiation, but there might be a corresponding effect on the whatever the effect of the falling charge is. Another argument, more cogent, I think, at the moment, is the principle of equivalence, which is the main point that I want to talk about. Now, there are many different statements in the general relativity literature and the special relativity literature called the equivalence principle. They differ by minor technical points and say something slightly different, and many of them actually say exactly the same thing, but emphasize different aspects of the physics. So I should make clear what I mean by the principle of equivalence, which I call the qualitative equivalence principle, or the Unruh-like equivalence principle. And it begins by general relativity teaches us that gravitation is equivalent to a combination of acceleration and curvature. The curvature of space-time are being unimportant on sufficiently strong space-time scales. So local experiments on a strong space-time scale exhibit gravitational effects, which are simply remnants of the acceleration of the frame in which you're describing the experiments. So in this limit of a very small lab, local experiments can be treated by special relativity, and any surviving gravitational effects can be removed or can be explained away as effects of your own acceleration. So curvature effects include what are known as tidal forces. Now, in the GR textbooks, the emphasis is on the explaining away. The lecture the student is given is just stick to true inertial frames and avoid confusing people by talking about fictitious forces. Gravity in the terrestrial sense doesn't really exist. It's there because you're accelerated if you're not falling into the earth. But it's also useful to turn this statement around and say that acceleration of the reference frame can be incorporated into special relativity by treating the accelerated frame, pretending that it was a legitimate inertial frame in special relativity, but adding some fictitious gravitational forces, which would include the mundane terrestrial gravity that we describe as falling, and also for linear acceleration, and also centrifugal and Coriolis forces from in the context of circular acceleration. So now, to see an important ramification of that, let's consider first that we accelerate things by some non-gravitational force. Suppose our lab contains a huge capacitor, and we put electric charges on the things so that they are accelerated by the capacitor, maybe our detectors as well, and assume we always balance them so that the acceleration is the same for all of the things we discuss. If it's not zero, then we could put the charge in the capacitor, or we could put the photon detector in the capacitor, or both, or neither. So there are really 4 experiments to be considered. So in these drawings, the left-hand side shows a floor or a table where things are at rest, and then on the right-hand side, the accelerator, the huge electrical capacitor that pulls things down. So on the left-hand picture, we think things that are sitting on a stationary table and things that are accelerated electrostatically. Then we would context let's go back and look at the picture. In case 2, we would say that we have a charge. The round red thing is the charge. On the right-hand side, it's being accelerated electrostatically. Our detector over on the left, then we would expect to see Larmor acceleration. In case 4, the detector is also inside the field, and we might wonder whether we really do see acceleration. I argued earlier that maybe we don't. In case 3, we have the case where the detector is accelerated and the charge is sitting still, and we would say that maybe the detector might observe some radiation from the charge simply by some kind of classical Unruh effect. But now let's suppose that the force causing acceleration is a gravitational force, and that is, we replace the capacitor by an elevator shaft and just accelerate things by tossing them into the shaft. Why should that make a difference? The local physics of the interaction of the charge with the local electromagnetic field and the radiation field and the atomic physics, if we have something, an atom that's radiating in the situation, it shouldn't depend on what is accelerating, whether the force is gravitational or electromagnetic. So we'd be tempted to look at these pictures that I just showed you and say exactly the same things that I said before, except that the force is gravitational. Or orthodox general relativity tells us that we should change our point of view in this situation about who's accelerating and to draw almost the same pictures but say different words. So now on the left-hand side, we have our stationary things, which are now stationary, meaning supported on a table in the lab. And so underneath, I don't know whether it shows up well enough on your screen, but you should see some little arrows down here that indicate that the lab table is being accelerated upward. Otherwise, it would fall into the earth or into a black hole if we were around a black hole. So we have attached rocket motors or just table legs underneath the platform to accelerate it upward. Whereas on the right-hand side, we have Einstein's elevator. Things that are in Einstein's elevator, by definition, are in free fall. So we still have a vertical direction downward that shows the direction in which the things move, but we say they're in free fall, not accelerated. So now in this situation, in case 2, we have let's look at case 3 first. The charge now is on the table and accelerated upward. The detector is over here in free fall. It is not experiencing any acceleration at all. The issue is, does it see radiation from the charge that's being accelerated? And some people find that very hard to take. In case 2, we have the situation where the charge is in free fall. The detector is accelerated, and we might say that we have might see some Unruh radiation. Case 4 is the one in which neither is accelerated, and case 1 is the case where both are accelerated, and now it's less obvious in this case which one is the one where there is no acceleration detected. So the upshot is that when we change our point of view about what acceleration means in a gravitational situation, what we used to call case 4 is now called case 1, and vice versa. What we first called case 2 is now case 3, and case 3 is now case 2. So if the equivalence principle holds, that means you don't have to worry about this. Case 1 and case 4 are essentially synonymous, and case 2 and case 3 are essentially synonymous in a qualitative sense. Then in case 1 and 4, there should be no radiation. And if you accept the consensus that the Larmor formula is correct, even for uniform acceleration, then the answers in case 2 and case 3 should be yes, acceleration is detected. Let's discuss this from a quantum point of view briefly. These are the same cartoons as before in the gravitational case, but now both objects are detectors. The square one is our detector. The round red one is some other detector that we're observing. Then case 2 corresponds to the Unruh effect. The detector is the red thing is actually in free fall, but the blue thing on the left, are being accelerated, so we should see some radiation. At the very least, we should see Unruh thermal bath, and possibly something extra coming from the presence of the detector. In case 3, we are not accelerated, but the red detector is accelerated, and so the Unruh Wald effect should come into effect. We should see the detector radiating. Case 1, in this case, everybody is accelerated. It's the case of coacceleration, and we would expect then that we don't see that Unruh Wald radiation ourselves. So you may not like that analogy. I admit it's a little forced, but there are some other quantum analogies that are much more directly related to the classical situation. And I recommend this sequence of 3 papers read in reverse chronological order to go from the simplest case to the most complicated case. The first, written with Justin Wilson, works with a mirror in 2-dimensional space-time and argues that a stationary mirror should radiate into the Rindler vacuum as seen by an accelerated detector. The second one talks about a static atom, which excites and emits photons into a Rindler vacuum corresponding to what's seen by an accelerated observer. And then the thing that gave rise to this whole thing is this paper by Marlon Scully and a cast of thousands in the proceedings of the National Academy, saying that an atom falling into a black hole emits Hawking-like radiation into the Bowler vacuum. This is a good time to make a remark that the symmetry between case 2 and case 3 in all these situations is only qualitative. You sometimes read, especially in elementary or popular expositions, that special relativity shows that velocity is relative, and general relativity shows that acceleration is relative in the same way. That's not quite right, because when you go from one Lorentz frame to another, the Lorentz transformation that takes you back to the original frame is another Lorentz transformation. It's the same as the Lorentz transformation you use to get into the new frame, except for the sign and the velocity. But if you take the Rindler coordinate transformation that relates Rindler coordinates to Minkowski coordinates and invert it, you get this, which is something totally different. So it's simply not true that the accelerated Rindler observer sees the Minkowski observer as something like a Rindler accelerated object. It's something quite different. Nevertheless, it is, I argue, qualitatively the same, and that makes the equivalence principle correct. So now let's really get down to work and consider a point charge whose trajectory is one of these Rindler hyperbolas, which I assume lasts for all time for simplicity. Then for that situation, Maxwell's equations have a unique retarded solution, which is a special case of the Lenard-Wiechert solution for a charge moving with an arbitrary acceleration, another development at the very end of the 19th century. This solution is known. You can write it down. So why are there controversies? Why can't we just look at the solution, which is at least 120 years old, and see where the radiation is? Well, the problem is, what is the definition of radiation? You quickly realize that this whole discussion is a matter of semantics. What does the word mean? And that's the main reason why the controversies keep going on generation after generation. And before getting down into any technical details of what we mean by radiation, I will state my students' conclusion without a detailed statement of the definition or the details of the calculation, and then get back to radiation at the end and cover it with as much detail as I can. But first of all, let's have a little history excursion. This solution that I'm talking about was first found by Max Born in 1909, and like most physicists of his age, he thought of the coordinate transformation just as algebraic formulas relating old coordinates to new coordinates or vice versa, and was not very precise about what the ranges of variables were. And it was Schott a few years later who noted that Born's solution couldn't possibly be true in all of space-time, because if it did, it would say that there was radiation back in those regions that I labeled R, L, and P, that it violated causality. So Schott said you have to cut off the solution at the horizon and use it only in solutions F and R. Then Bondi and Gold later on realized that there's more to this story than that. If you're dealing with the vector potential or with the solution of the scalar analog that's something that satisfies the Klein-Gordon equation, then just taking the Born type solution and chopping it off, setting it equal to 0 in the past is correct. But the electromagnetic field comes from differentiating the vector potential. And so the Schott solution really includes also a delta function field that is located right on the past horizon. And Bondi and Gold, as I recall, did not talk about the delta function as the derivative of a distributional derivative of a step function. They just gave some physical arguments. I shouldn't say just. They gave some physical arguments and realized what that solution had to be for consistency, and gave the physical interpretation that it had the burst of energy along the horizon had to be the cumulative effect of all of the emission that would have come from the solution, from the charge at very early times, going back to infinity. Then the really crucial work was done by Fritz Rohrlich in this trilogy of papers written in the early 1960s. The first one was in collaboration with a protege named Fulton. And then Rohrlich continued to work on this for the next few years and wrote 2 other papers in which he changed his mind about some things. And so as you go along, the papers contradict each other, but he finally came up with a consistent picture. He wrote a book about it, which has developed into 3 editions as he changed his mind still more. But to my taste, the 2 last papers here in the list are more valuable to read than the book. The book was written as a graduate textbook, which covers a lot of other electromagnetism beside the part that we're interested in, and doesn't get quite as detailed as I would like about the things that are relevant to the principle of equivalence. So let me pause to remark that the 2 names that I mention most often in the history are Rohrlich and Rindler. And I was struck by the fact that their lifespans almost exactly coincided. Unfortunately, it seems that they didn't talk very much with each other. So Rohrlich, I believe, never really understood horizons or the significance of horizons. And so you have to wait another 15 years for the crucial paper of Bowler, which is in some ways the culmination of this subject, that it discussed the problem of acceleration from a uniformly accelerated charge in the modern context of horizons. And the subject didn't stop there. I told you that my student has written a thesis, which, with the result that I'm about to report, he wrote of his work, and then a week later came back and said, I've discovered that this is all in the literature by these people who studied an arbitrary accelerations, and I can take their equations and apply it to my situation and get my result. And I said, well, great, but I like your result better because it did it directly, and I don't know other people who know much about these other papers, so don't worry about it. It's still great. What you did is still great and important work. And so it's going to be in one part of his thesis, which has other things in it as well. But the center point centerpiece of what I want to talk about today. So as I say, I'm running out of time, and so I will simply present the result, and then we'll talk about where it came from, and later on to the extent that there is time. So we consider a point charge Q that's moving with proper acceleration A. And he says, let's consider not just one hyperbola, not even just one Rindler frame, but a whole family of Rindler frames parameterized by two parameters chi0 and g, and it has coordinates chi. Each one has coordinates chi and tau, and those coordinates are related to the fixed inertial frame coordinates t and z by these equations, which involve a parameter g, which is almost always in there to make the dimensions correct, and is in some sense an acceleration, but acceleration of what? It depends on which hyperbola you're talking about in the Rindler system. And then there's additional parameter chi0 that tells how this Rindler coordinate system is offset from the inertial coordinates. Why is that important? Well, here, this is the coordinate, the metric that you get in the Rindler coordinate systems. And now he says, let's choose the inertial coordinates once and for all so that the charge we're considering passes through the origin of that Minkowski coordinate system and is instantaneously at rest there. But it has acceleration A in the z direction. Now we'll choose the chi0 in the Rindler coordinate system so that this Minkowski origin is sitting at chi equals chi0 in the Rindler system. I want to stress that the parameters chi and g are somewhat redundant. You can normalize the Rindler coordinates so that either g equals 1 or chi0 equals 1. Conceptually, chi0 is more important since it represents the displacement of the horizon vertex from the charge in the negative direction, because we want the charge to be inside the Rindler red. So it looks like this. The red thing is the trajectory of the charge, which passes through the origin of the xt system at this point. And so to lowest order, or to second order, it's a hyperbola. However, it's drawn not as a hyperbola at other times, because it's good to understand that the charge's acceleration in this discussion need not be uniform. We are going to consider only the instant when it goes through the origin, and that's what happens as seen from these Rindler coordinates. So the conclusion that is reached, and I suppress the entire calculation, it can be found in Luther's thesis when it's available, are extracted from the papers by Kretschmar and Fugman and Gariyama. And in principle, it goes back to Rohrlich's papers, as I cited before. The conclusion is that in one of these Rindler frames, the total power being radiated by the charge at the instant it passes through the inertial origin, which is all you need to consider because we have a massless photon field, and so the radiation moves along light cones. If you give the field a mass, then things become more complicated, much more difficult to discuss, because the radiation that you're seeing at one instant doesn't always come from the same spot on the trajectory. But anyway, the formula for the radiated power is equal to times A minus this other acceleration over here squared, where A, recall, is the acceleration of the charge itself, and G over chi0 is the proper acceleration of the hyperbolic world line in the Rindler coordinates that passes through the location of the charge. So if you follow my advice, do my homework problem, and rescale the coordinates to make chi0 equal to 1, then you get this nice, beautiful, simple formula that says P is this Larmor constant times the square of a minus g, the square of the difference between the accelerations. So the two accelerations come in and play exactly the same role. If the two accelerations are equal, then there is no radiation, which vindicates our previous consensus that if the observer coaccelerates, there is no radiation calculated or detected. If A is 0, we're saying the charge is stationary, but nevertheless the radiation is proportional to g squared. So the charge radiates from the point of view of the accelerated Rindler observers. So that vindicates the case 2 or case 3, whichever one that you're thinking of, where the most controversial part of the qualitative equivalence principle. The charge sitting on the table in the lab does radiate from the point of view of a falling detector. The third special case is G equals 0, which actually is not legitimate in the way the coordinate system is set up, because it's a limit, but it represents a Rindler frame with the horizon so far removed from the charge that the frame is effectively inertial. So that's how an inertial frame fits into the formalism here, and the result is just the standard Larmor formula as expected. So now let me do what I can to argue that we have a sensible definition of radiation that does lead to this conclusion. Your first attempt at defining radiation, and this is actually what you find in some books and papers, radiation simply means a non-zero pointing vector at your detector. But a few seconds contemplation shows that surely must be wrong, because that would say that if you have a charge just sitting there and its field is a Coulomb field, and you go into a moving frame, a Lorentz frame that's moving with constant uniform velocity, then you would say that charge is radiating. But surely we don't believe that. That's not what we want. We don't want to say there's radiation in that case. And in fact, there's no energy loss. And the proof is you take a more sophisticated point of view and say that this Poynting flux has significance only if I integrate it over a closed surface surrounding the charge. And then I will see that in the case of uniform motion, the energy that the charge pushes out of the surface ahead of it is precisely canceled by energy flux coming in with the opposite sign on the backside of the closed surface. So we should do the same thing for the case of acceleration, and choose a surface that surrounds the accelerating charge in some sense. But that means that if we look at the Poynting vector at lots of different points on this surface, that means that they will be on different hyperbolas of the Rindler coordinate system. So we aren't really considering a single observer or a single detector, but a whole ensemble of them that belong to the same Rindler coordinate system. But as I stressed earlier, that doesn't mean they have the same physical acceleration if they're detectors at different points in space-time. This is why you do have to consider Rindler coordinates and get an acceleration effect rather than just Lorentz transformations. If we were just interested in the Poynting vector at a particular point in space-time, then the fact that we're in motion would simply mean that we'd need to go to a different Lorentz frame. There would be no Rindler coordinates involved. It's only because we have a somewhat non-local construction of integrating over an entire closed surface that we have to consider the acceleration and the corresponding hyperbolic structure of the coordinates.
It's been 45 minutes, okay?
Okay. So we have, in this situation, let's look at our cartoon again of the situation. I've now added a surface of constant Rindler time. The Rindler space R is, of course, a proper subset of the Minkowski space M, just 25% of it. And the reverse is certainly true. So this qualitative equivalence principle is certainly not going to be obvious. In the Rindler region, the natural time slices are slanted planes, as I've drawn, and that natural time-like killing vector is along the hyperbolas that are orthogonal to those planes. And following Röhrlich and all those other people that came in between, Luther Rinehart studies the Poynting flux, defined by contracting the stress tensor, which comes from the Born solution, with the killing vector that's appropriate to the situation, and then calculating the flux through the surface of integration, which means saturating the other index of the stress tensor with the unit normal vector to the surface. So you can do that for the Minkowski space, the ordinary inertial frames, but you can also do it for the Rindler frame. So the Xi is a boost generator in the terms of special relativity, and S is the flux of boost energy, not ordinary Cartesian energy. But both of them are conserved quantities. But the fact that it's the boost energy and the Cartesian energy are not the same thing suddenly makes it clear how you could get a different answer for accelerated observers as opposed to inertial observers. And let me emphasize, all of this came into general relativity by analogy with the Schwarzschild black hole, right? So outside the Schwarzschild black hole, this hyperbolic accelerated killing vector is the only killing vector we have. There is no Kruskal killing vector corresponding to free fall. So this is the only conserved energy we have. That's why this question is such central importance in the context of general relativity. So we look at our integration surface, and this is a ton of words. Let me show you another picture, which I'll come back to several times, and try to argue that the words correspond to that picture. Take our integration surface to be the intersection of the light cone of a given point on the world line, which is the point that is radiating, whose radiation we want to study, and look at the intersection of the light cone coming out of that point into the future on the surface of constant time. And I can do it either with Minkowski time, getting the usual situation, or I can do Rindler time. And Röhrlich observed in his second paper, contradicting his first paper, that, and somehow you have to assume that the field you're dealing with is the retarded solution from that charge distribution. This flux integral is independent of the time slice. Or to put it another way, it's independent of the radius of the sphere. The terms in the Poynting flux that fall off faster than the distance, the inverse square of the distance, turn out to be orthogonal to the surface if the surface of a sphere in the right place. So contrary to what you might think and what you sometimes hear, you don't need to go out to infinity in order to define or calculate the radiation. That's really good, because our discussion of the equivalence principle demands that we be close by, right? So if radiation had a meaning only at infinity, there would be a problem or a solution, depending on your point of view, solution paradox. So in the Rindler case, this is what happens to those spheres, because you're going to more and more slanted surfaces. So the spheres are not centered on the charge. They're shifted like this, and they never get far enough, really far away in the direction back toward the horizon. Okay, so that's the basic conclusion. And now there are two things that I say you should still be worried about. The first is the famous observation that inside the region R, the solution is invariant under time reversal. The retarded solution and the advanced solution are identical there. So that inside the region R, you don't have radiation coming off in this naive picture over here from the charge that we would think you would have from the Larmor formula. Instead, you have this picture that I drew originally, where the radiation is up in quadrant F, and there's also this Bondi gold radiation along the past horizon, but nothing in the interior of the region R. Bowler tried to explain this by saying that there are fluxes of inertial energy inside R, but they can't be interpreted as radiation because they're both incoming and outgoing. And when you look at the energy, the Minkowski energy, they're non-trivial, but they cancel so that there's no change in the total energy. So the incoming flux is somehow, where does it come from? He says it's somehow released from that singular burst on the back horizon, this part here, which was emitted by the charge at earlier times. My other student, the undergraduate, wrote in his thesis, shows that when you include the transverse directions, this does not violate energy or momentum conservation in the field, which I thought would be true. But exactly how this miracle occurs is something I still don't understand. So I think it needs further study. The second loose end is, okay, we accept that radiation in region F is compatible with time symmetry, time reversal symmetry in R, and a co-accelerating observer is never in F, and so it never sees the radiation in some sense. Nevertheless, how can I turn it around and get the equivalence principle? How can I say that radiation is observed by a detector that's moving along this dotted trajectory from a stationary charge that sits here, moving along a totally inertial world line? I can't say now that there's some part of R that is not part of the Minkowski space, where there is radiation when there's no radiation in Minkowski space. Something else is going on. And this paradox seems to be somehow inverse to the one about the Coulomb field with unified velocity, which I resolved by saying that the flux in turns out to be equal to the flux out. So presumably the resolution of this one is quite similar, using the spatial asymmetry of the light spheres, that this feeling of a Rindler space calculation developed this eccentricity on the side facing the horizon. They never really get very far away from the charge. And so there's a scope for a lot more going out than flux going out than coming in. But a lot more needs to be done to demonstrate that quantitatively in a way that it intuitively makes sense to me. So that's why one reason why I didn't write a conclusion slide. I don't consider the conclusions entirely finished. So I stop here and thank you for your attention.
So thank you very much for your talk. We've got time for a few questions. Mike Good, I think, yeah, go ahead, please.
I would love to ask a question about the the G equals 0 in that, in the beautiful expression that you have, where A minus G squared, you have one of the examples where G is equal to 0, but you need to take a limit. And you mentioned that it was related to, that this formalism would work. For any arbitrary acceleration, it need not be uniform. Does this limit, could maybe you elaborate on a little bit on that, because it seems as if G equals 0, not having to be a limit may have some consequence for, asymptotic inertia in this.
Okay, Mike, I must apologize that I'm trying to listen to you and read the chat at the same time. So I'd like to dispose of the chat first and then come back and let you ask it again if necessary, if I don't give a comprehensible answer. Somebody's pointed out that I believe, okay, this is my student's name, Tim Bates. Did I say something else earlier? There's also a Tim Bunch who worked with me 40 years ago. So Balak says that I called him Tim Bunch at the beginning. If so, I'll correct the slides sometime. Okay, so let's go to Mike's question, which was
the G.
Yeah, okay. Okay, so, right, so taking G equals 0 is the same as taking chi 0 to infinity, because this is really the most general formula, right? Now, what happens when you take chi 0 to infinity? It means that you're moving this, if you keep the charge fixed, you're moving this vertex way, way off to the left. So you're going out to the region where the Rindler coordinates are on a very small scale, almost Cartesian. Not as fast as happens in Schwarzschild, where you really do get to ultimately to essentially Minkowski situation, but still, it's the closest thing you could get within this framework to a Cartesian system within the other system. So did I answer the question?
Kind of. I guess my worry is that you're saying it need not be uniform, but I'm curious how it actually, how uniform is okay to use if it's eternal.
Oh, this one. Yeah. But I would be perfectly happy to keep this discussion today in terms of uniform acceleration. But Luther drew this figure, and he convinced me, yes, all we're talking about in this discussion is this one point, radiation from that one point. And from that, the Unruh-like solution applies. You don't really need to know anything except the acceleration at that time, at that proper time, in order for the Unruh-like solution to hold. Now, the other part of Luther's thesis has to do, which I didn't talk about, has to do with what happened if you give the photon a mass and look at the Proca field in this context. That makes things more complicated, as I said, because now radiation spreads out into the entire future light cone to some extent. But the advantage, the reason we want to do that is that it allows you to turn the charge on and off without violating gauge invariance. And that might help someday in understanding the exactly what's happening when you go from eternal acceleration to something more like this. Because I would rather not consider a path like this. I'd rather consider a hyperbolic path, an eternal hyperbolic path, but turn the charge on and off. Because that's a simpler problem mathematically to look at, but for a scalar field with a scalar source, but with the electromagnetic case, the turning the charge on and off is inconsistent with Maxwell's equations. So you have to modify Maxwell's equations somehow, and the most covariant way to do that is to give the field a mass, and then you no longer get a contradiction with it when the charge is time dependent.
Well, that's very interesting. It's some good food for thought with this, without violating gauge invariance. I like that. Thank you.
Okay, there is one more question by Adrián del Río, so please.
Yes, thank you for this very nice talk. So the question I had was, so you asked the question several times during this talk about how to define radiation. And so this reminds me, so that the same question was asked in the context of general relativity to understand the issue of, whether TR admits gravitational waves or not. And the answer essentially was given in the context of asymptotically flat spacetimes by introducing, this work by Bondi, Sachs, and later by Penrose and so on, the framework of Scribe-Plus. So essentially in this context, the answer to whether there is or there is not radiation is essentially the statement of whether there is a flux or whether there is not a flux of energy flowing across Scribe-Plus, so infinity. So my question is, could one rephrase some of these questions that you have posed in this talk within this framework? Would it be helpful to employ this formalism to see if that helps in clarifying some issues, or is hopeless for some reason?
Well, I think your remark may be relevant to this situation because the formula that I presented satisfies the qualitative equivalence principle. Although from a physical point of view, it's hard to understand in this situation why there should not be any radiation. While there should be radiation, when there is the field that we're looking at is a pure Coulomb field, and I argued that it had something to do with this, and unfortunately I don't have a good figure to make the point that I want to make. Where's my this one. So okay. We're stuck inside R, right? If we're talking about the Rindler approach to defining observables, and so we move up here. Say we never really get outside R, so in some sense we're not getting to scry. Certainly not getting this part of scry over here.
Right.
Does that matter? Well, in some sense, no, because its result of Röhrlich says that the radiation that you calculate by looking at in Minkowski space by looking at a sphere way out here is equal to what you would calculate if you work along a tiny sphere somewhere closer, which could stay entirely inside the Rindler region, especially if you're moving to a later. If you're staying in the Rindler system where the natural sphere will go out a long way over here and not so far over here. And I am not completely satisfied that the calculations that you do on these Rindler spheres really correspond physically to radiation. I change my mind about it from week to week.
So
how to fit this into what what Penrose said about gravitational radiation, I will not pontificate on that. But I thank you for bringing it up, and leave it to everybody as homework to improve this, to keep improving our understanding of this situation. We've been at it for 120 years. We can continue to make discoveries and improve formulations.
Okay.
So we've got another quick question, if you don't mind. Please, Ariel, go ahead.
Yes, if you can just put the one with the global loose end number 1, where you discuss the retarded and advanced solution.
Oh, you're still talking to me?
Yes.
I thought you were the next speaker. I'm sorry. Let me share the screen again. I had hurriedly removed myself so I wouldn't get in your way. Okay, here's my screen again. Now, which one did you?
It was the global loose end number 1.
Global loose end number 1. Okay, let's.
Yeah.
Okay, yes.
Yes. So I found your remark there very interesting in the sense of the time reversal. So the fact that you have the retarded and advanced solution, and I'm just wondering if the concept of entropy can help us understand this aspect, because the entropy would be the fact that you would have an irreversible case, so no time reversal. So the Rindler horizon, I believe, would have an entropy associated with it. So I'm just wondering if the concept of entropy can help understand this result.
Well, I'll have to say I don't have the foggiest idea. More power to you if you can say something interesting on that.